All right, guys. So I'm going to start the lesson on sound. So we've talked about sound a little bit in previous lessons, like the first one of this unit, where it's a longitudinal wave, but we're going to get more specific with it. So sound's a longitudinal wave. It generally travels in the air around 340 meters per second. So it's pretty fast, but not as fast as like light, which is much, much faster. Um, it travels through other media. So what that means is it travels through different types of substances. So it can travel through air, it can travel through vibrations in materials like liquids or solids. So, and it changes its speed based on what it's vibrating through. So sound waves are started by a vibration of some sort. So the way that sound is coming to you from me is through my voice box vibrating. And that vibrates the air, and that air vibrates and it gets all the way to your ear, and it your ear detects it. In the next activity that we're going to do towards the end of the sound lesson, you're going to learn more about like how the ear perceives sound. So I have a little GIF down here, and it's showing you a longitudinal wave. So we talked about longitudinal waves before with compressions and rarefactions. So the compression is where those particles are shoved close together, and the rarefaction is where it's kind of spread out. So you can see the wave moving again. So waves carry energy from one point through a material to another point. And then the actual particle that is vibrating or bouncing back and forth isn't moving that much. So you see the red dots kind of keep oscillating back and forth between the same points. So those are like air particles if we're talking about sound going through air. Sound also just follows the same normal wave equation that we talked about. So the speed of a wave is v equals f lambda. So continuing on, again, it's affected by the medium that it goes through. The more closely packed the particles, the faster the sound moves, because that makes sense, right? So like there's less distance between the particles if they're closely packed. So the sound wave can travel through it more rapidly, whereas in other substances that are less packed, it would take longer. So just kind of going through a problem real quick here. It says the sound is traveling at 330 meters per second, has a frequency of 440 hertz, and we're looking for the wavelength. So just reviewing that equation that I showed you on the last page, v equals f lambda. V is the velocity of the wave, so that's going to be the 330. And f is the frequency, so the frequency said it was 440. And the wavelength is the symbol lambda. So that's that symbol if I draw it. And what you would do is you would divide by the 440 on both sides, and you should get a wavelength of something like 0.75 meters. So kind of going back and showing you like a wavelength on this screen. So like you see how these compressed particles are kind of moving to the right. So like the wavelength would be the distance between those particles. Okay, so so that's that. The other question here on this page says, rank the following from fastest to slowest in terms of the rate at which sound will travel through. So we have air, a vacuum, wood, and water. So if we're just kind of thinking about the materials themselves, air is a gas. So hopefully you remember some ideas about how gas particles are in relationship to, say, wood, which is a solid, and then water, which is a liquid. So if you think about a vacuum has no particles, so it's like an absence of matter. So it's not any substance. So it's not a solid, it's not a liquid, it's not a gas, it's nothing. So if there's no substance there, the sound wave is not going to travel through it. So the vacuum is the slowest. So I'm going to put vacuum all the way over to the right as like the slowest when we're going from fast to slow, because the sound waves actually wouldn't travel through a vacuum because there's nothing to run into. There's nothing to vibrate in a vacuum. So the vacuum is last. And like if you watch any sci-fi movies, like I don't know, anything that goes into outer space and they have like a giant explosion and it makes a lot of noise. In space, it wouldn't do that because there's nothing to vibrate to make that noise. So, so going from fastest to slowest, we got to think about which one has the particles that are most tightly packed. So we have a solid, a liquid, and a gas. So hopefully you recognize that like a solid is going to be the most tightly packed of those particles. And then second would be the liquid. And finally, third would be a gas. So I don't know if you've seen like old movies, old Westerns, or movies that kind of where they put their ear to the ground and try to listen to see if somebody's like following them, or if there's like they might like go and touch a train rail to see if like a train is coming. That's because the wave will actually travel faster through the solid, like the ground or the train rail, compared to going through the air, which would be the gas. Okay, so that's sort of it. And when it travels at different speeds, it sort of changes the perceived frequency. So like if you try to listen underwater to somebody talking, it sounds different than it does in air, because again, it's vibrating at different frequencies that sound different. Okay, so one thing that all waves do, they have a measurement of intensity. So intensity is sort of like how strong the wave is. It's sort of like amplitude. It's a rate at which energy flows through an area. So it's like the amplitude per area, sort of. That's another way you can look at it. Intensity is measured in something called decibels. So you probably heard that. It's like a rating of how intense a sound is. And the human ear can detect sounds that are from 0 to 180 decibels. If you're trying to figure out like how loud something is, if somebody's whispering at you, that's about 10 to 20 decibels. And then if you were standing next to like a jet taking off or a rock concert, that's about 120 decibels. So it's not a linear scale, it's like logarithmic, but you don't have to worry about that. So your ear perceives intensity with loudness. So when you hear something as loud or soft, that's your individual ear detecting the intensity. And you'll learn more about this in the videos later on that you're going to do for activity 11. But every person has a different kind of response to the intensity of sound. So like if you have any older relatives that are hard of hearing, basically they don't pick up the loudness. So the sound is still the same intensity, but their ear doesn't perceive it to be loud. So like my father is hard of hearing, so we have to talk really loud around him, and the intensity has to be bigger so that he can perceive it. Another thing that your ear perceives is pitch. So if you're in any sort of music band or chorus, then you've probably talked about pitch before. And it's the frequency of the sound. So it's like how high or how low a sound is. And again, humans detect between 20 and 20,000 hertz generally. And that changes as you get older too. So as you get older, your frequency detection gets less and less. So you can't hear quite as high of frequencies. Then there's a sound that is actually outside of the perception of humans. So sounds that are higher than 20,000 hertz, those are called ultrasonic, and those are used in ultrasound or sonar kind of waves. So they're really like super, well, not super high, but very high frequency that your ear doesn't pick up, but you can see kind of the sound wave vibrating off of something else. Okay, so one thing that is talking about frequency, and I'm going to use an example here that hopefully you're going to be able to hear, is the Doppler effect. So you might have heard of the Doppler effect. It's the changing in apparent frequency of a wave as a result of motion of like a source, an observer, or both. So we're going to watch a little video really quick and kind of show you what, or so you can perceive what that is. And then I'll come back and explain kind of the idea, and we'll try to answer this question. So let me click on this link and see if it comes up like it's supposed to. Hopefully you're still seeing this. And I'm going to have to wait for the commercial, sorry.
One of my least favorite things about writing papers in college was remembering the correct format for my...
Okay.
Good morning. The Doppler effect is named after Christian Doppler, a 19th century mathematician and physicist who was able to mathematically describe what is now called the Doppler effect. And it sounds like this.
Okay, so let me get rid of that and get back to our lesson. So what I want to point out is the Doppler effect is the shift in the pitch. So it's like the frequency. So you hear like a higher pitch and then a lower pitch. It's not the loudness of it. So like obviously as the car got louder, or as it got closer, it gets louder because that's how the intensity works. But the idea of like how high or low the sound is. So if it's a low sound or a high sound, like I can't do a high sound really that well, but that's the idea. So so the way it works is If you imagine this is like the fire truck or the car with the horn on, as the car moves towards the observer, so let's say the car is moving to the right, and I am the observer over here listening, the wave, so like if it's just sitting still, then the wave is very normal and regular, and you would hear the same tone the whole time. So like the sound waves that go out and they have them as circles or ovals here, they would be consistent and be the same distance as as it keeps releasing sound. But as you get closer, as like the two objects become closer, then this person is going to perceive a higher frequency. So the higher the pitch. So if it's coming closer towards you, then you would perceive a higher pitch, and that's what you observed with the car moving towards the camera. And then as it moved past, the sound wave gets spread out because it's moving away, and it gets more and more stretched out, so it gets to be a lower pitch. So that's why this is a lower frequency on this side. So some ways that you can cause higher frequencies. So that would, you want to like the things to come towards each other. So you could have the object moving, or the source of the sound. Let me type this. The source is going toward the observer. That's one. The observer. So like I could be going towards the source. That's another one. Or you could have both moving towards each other. So those are the three possibilities that you can get a higher frequency. So like you can have just the car moving towards the person. The car could be sitting still, and you could have the person moving towards the car. That's going to, again, make the waves kind of get jammed together in higher frequency. And then finally, you could have both of them moving towards each other. That's the other option. All right. So the next part of the lesson we're going to talk about is what's called interference. So sound waves, like every other waves, like they can go through each other. So if you imagine like making waves in a pool, so somebody's pushing a wave one way and somebody's pushing a wave the other, like they run into each other and they make kind of a bigger wave or a smaller wave depending on that. So when two waves pass through each other, the resulting displacement, or the resulting kind of like amplitude, is the what's called interference. So interference in sound waves causes an increase or decrease in amplitude. So things sound louder or softer based on this interference. So there's a whole like group of like noise canceling headphones and technology that is trying to like cancel out waves. So the way they work is they have what's called destructive interference. Acoustics and the way people design rooms, where they like, so like maybe like auditoriums or concert venues, they try to make it so that there's constructive interference at the seats and it makes it louder. So that's what they try to do. So here are some visuals of that. So these two waves up here, that's going through constructive interference. So if you imagine the two hills are going towards each other, when they run into each other, it makes a bigger wave. So if you just follow like that overview, so the small wave and big wave run into each other and you get a bigger wave. So that's constructive interference. Destructive interference is sort of the opposite. So like they're on opposite sides and they're going to cancel each out. So when they cancel each other out, if you look here, and again, when they come back, it goes a little slower. Then the wave actually goes to nothing. So like as they pass through each other right about now, it canceled out for a second. Okay. So that's constructive and destructive interference. You basically just got to kind of look at those and be able to say, oh, well, yeah, it's going to make a bigger wave or it's going to make a smaller wave. And it's all about, are they on the same side or opposite side? So one phenomena with sound that goes along with this, and this is probably the last idea that we're going to talk about, is what's called beat frequencies, or beats. So beats is the word physicists use to describe the characteristically like loud, soft pattern that characterizes two nearly but not exact match frequencies. So that sounds like a lot, but if you're in band or chorus, it's basically like being out of tune. So it's kind of a vibration of like loud and soft, or like an alternation between loud and soft. So I'm going to again use a website to help demonstrate this. So first, I'm just going to start where they're in tune. So if I had two different waves, so there's going to be like a frequency of 250 and a frequency of 250. And if I play them at the same time, you can hopefully hear that kind of dull, like wah sound. So they're in tune, so there's not any difference. But like if I just change the frequency a little bit, so I'm going to make this 252. So like the red wave has a slightly different frequency than the blue wave. And when I turn them on, you can hopefully hear that wah, 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 that loud and soft alternating. So that's a beat frequency. or the beats. If I change it to like a different number, so I could make it like they're 3 apart here, you'll hear more wobbles. So it's 1, 2, 3, 1, 2, 3. So that's how it works. So the idea is like whatever the difference in those frequencies is, and I'll stop that because it gets pretty annoying pretty quickly. The difference in these two frequencies, so I had 250 and 247. So if I did this in the math, so it doesn't matter which way you put it, it's the absolute value. So if I put 250 minus 247, the beat frequency is just going to be 3 hertz. So 3 hertz means that you hear that wobble 3 times per second. So if we go back to that site and I listen to this again, you'll hear those wobbles. And if we change it to like a bigger difference, so let's like at 245 and try it, you hear how it alternates quicker. And if I made it like closer in frequency, and so there's less, so it's wah, wah, wah. So that's what your band director or your choir director, when people are out of tune, they're trying to get rid of that like loud and soft alternation. Okay, so that's like sound, the general ideas, a lot of the big ideas with going on with sound. Let me show you the last thing that I want to take you to, which is, I might not have it up, hold on. I don't. So what we're going to do though is for the last activity, we have a couple sites that I found that have really good kind of presentations about the ideas of sound and how the ear perceives sound. And I think that's pretty interesting to most people. So instead of having like a simulation lab where you're collecting data and things like that, you're going to basically go through a PowerPoint and it has some videos in it. So you'll watch a little bit of the video, you'll try to understand those ideas. We've talked about some of them already, but there are a couple interactives where you'll put some frequencies in and you'll do a couple tests, but you're gonna use those resources. So that's what we're gonna focus in on the next class. So hopefully that's good. And let me stop sharing. So have a great day and I will see you guys later.